Hello, my name is Mogens Christensen and I'm from Aarhus University in Denmark. I'll give you an introductory lecture to application of X-rays and neutron scatters. So the general problem that humanity is facing is that the population is growing very fast. And this means that we have some grand challenges with regards to getting food, water and energy for everyone. And this talk will be about how materials can help and how the detailed study of materials can make better materials. So if we look at materials interconversion, it's possible to interconvert between electricity and other sources of energy or storage. So what I'm showing here is, for instance, if you have photovoltaics, you can interchange between electricity and light. So photovoltaics is a semiconductor, but by the generation of electron-hole pairs, you can either, from the light of the sun, create energy, or you can make an LED light bulb light up. But the principle behind is the same. Another example is fuel cells and hydrogen storage. Here we can store electrical energy in the chemical bond, and we need an ion conductor to actually change the hydrogen into energy. So here is like a cycle where you have the energy stored in the materials, you extract the hydrogen, put it into the fuel cell, and then you get energy and water. And this water you can then again use sunlight to produce hydrogen, and that hydrogen you can store in a material, and in this way the circle goes around and we have energy for everyone. Another common way of storing energy is in lithium-ion batteries. So this is now a lithium-ion conductor that can store the lithium ions in the anode and the cathode. If we go on, then thermoelectricity is a way that we can interchange electricity into heat and cooling. And again, here we need a semiconductor to carry this out. And the final example I have here is magnetism. So with magnetism, you can couple electricity and motion. So this is basically what happens in a dynamo at a power station and at other places like a car, where the electric motor is given electricity and then the magnet is actually transforming the electricity into motion. So for magnets, we need unpaired electrons. So this is typically from the rare earth elements or for transition metals. So I should have said that the two items that I will speak most about is thermoelectricity and magnetic materials during my lectures. So if we look at materials, we can sort of divide it into having materials here in the center, and then the materials have certain property. They are produced by a certain synthesis method, and then they have a certain structure. And the disciplines that sort of interlinks these different structure properties is materials chemistry, materials crystallography, and materials physics. So in the talks I'm going to give, I'll be mostly focusing on materials chemistry and materials crystallography. Taking a look at how to design a material, this is Lego bricks that we are quite famous for in Denmark, and you can basically build any shape or structure out of Lego bricks. And it's pretty much the same with atoms. If we take 1 gram of iron, this is equal to 10 to the 22nd number of atoms. Now, 10 to the 22nd, that's a really high number. What does that correspond to? Well, some people says it's the number of grains, sand grains in the Sahara Desert, which is 9 million square kilometers, or the number of stars in the universe. Both are really difficult to compare to. But 1 gram of iron is actually the same as a cube, which is 5 by 5 by 5 millimeters. Now, if I take that cube and actually enhance it by 1 million, I get something that is 5 nanometer big. And what I'm showing here is a nano big on each side. So this is how a crystal looks, or how the material iron looks at the nanoscale. Now this is still quite complicated, and to reduce the problem, we can then enhance the size by a factor of 10 more, and then we get the unit cell. So this is the smallest repetitive unit that we can find in the material. The material is basically made up of this unit cell that repeats over and over again. Now, what's interesting about iron? Well, if we add just 2% of carbon, we can completely change the properties of the material, and it turns into steel that is corrosion free and has quite different elastical properties compared to iron. So if you look at it, steel contains typically less than 2% of carbon, but could you imagine to put something else inside? Well, yes, as I was mentioning before, if we add some chromium and nickel, molybdenum, on top of the steel, we can make the stainless steel that doesn't rust. And you see, this also changes the melting point of the steel. Finally, which is a relatively new type of steel, has a lot of tungsten in it. And the special ability of this tungsten steel is that it has a very high melting point. So this is used in jet engines for airplanes. So the idea here is just to show you that relatively small changes in the chemistry can give you quite big changes in the physical properties, and then what application these materials can be used for. But a lot of the knowledge here is actually on the atomic level. How are the atoms interlinked to each other? So just a relatively recent interesting story was in brief communications in Nature, where they found out that there's actually carbon nanotubes in ancient Damascus blades. Now, Damascus blades was used by the Arabs when they fought the Crusaders. So already at that time they knew about, or actually they didn't know about it, but they were capable of using nanostructured materials to make blades that were harder and more flexible. Unfortunately, the way of producing these blades have over time been lost, but it definitely gave the Crusaders a headache when they tried to conquer the Holy Land. Now, if we want to look at where the atoms are and what they do, we can use X-rays and neutron scattering. So basically the region we want to look at is from something like 10 to the minus 8 to 10 to the minus 10th. This is where we have our atomic structure. And here you basically see various methods that you can use to investigate this region of space. To investigate the region, you have to have a probing tool on the same wavelength, or the same length scale. And here you see electromagnetic radiation, where molecules and atoms are found in a range scale of the X-ray and ultraviolet light. So this is the kind of photons we need to use if we want to probe this length scale. So very briefly, last year we were celebrating 100 years anniversary of X-ray diffraction. So the first experiment was carried out by Max Theodor Felix von Laue, better known as von Laue, and he received the Nobel Prize in 1914. And you see his results down here. They're not that convincing, but this is actually the first powder diffraction pattern ever collected. Things went quite fast from here. Lawrence and William Henry Bragg, they actually saw the results by von Laue and realized that it was not completely right, his theory. So they quickly made new experiments, and they were able to then deduce Bragg's law. And they received the Nobel Prize just 1 year after von Laue. Then some years later, about 20 years later, Peter Debye also received the Debye method for one of the things to actually develop the Debye-Sharra method. Now, the Debye-Sharra method is a method to actually measure powder samples, where von Laue and the Braggs were looking at single crystals. Debye and Paul Sharra was actually looking at powder samples. Now, actually already in 1918, Paul Scherrer was suggesting that the size of a particle can be determined from Newton's scattering. This is the title of the original paper that appeared in the Royal magazine. You can translate it into something: determine the size and inner structure of particles with X-rays. Now, actually 3 of these guys now have a neutron facility named after them. So we have the Institut Laue-Langevin in France, we have the Bragg Institute in Australia, and we have the Paul Scherrer Institute in Switzerland. So that was diffraction in about 100 seconds. So I'll go into much more detail. But before that, I hope that you will go through and read chapter 1 in the book Powder Diffraction Theory and Practices that I have given you. There's a lot of information from the powder diffraction data. So you see a powder pattern at the bottom here, but there's a lot of things that you can deduce, like lattice parameters, atomic arrangement, displacement factors, crystallite size, strain, texture, and relative phase fractions if you have more than one phase in your sample. Some other literature that I have given you is pitfalls in the characterization of nanoporous and nanosized materials. This gives a very good introduction to nanomaterials, and this will be the main topic in the second week. Basically, you can imagine 4 different kinds of interaction between a particle and a material. Oh, sorry, 3. So if you have an incident wave with a wave vector ki, it propagates through space. One of the simplest things you can imagine is absorption. So if there is something in the way of the beam, it will get reduced when it comes to the other side. Another option is scattering. So the beam hits the sample and then it scatters out in a certain direction with a certain final wave vector, kf. The last thing is refraction, where you have a bending of the beam. This is, for instance, used in glasses that corrects for near and far-sighted. The thing that we will discuss the most during these lectures is scattering. 2 other papers you have been given is on thermoelectrics. So one is a more general thermoelectric background, and that's from this review article from Asia Materials from the Nature Publishing Group. And the other one is taken from the Handbook of Thermoelectrics, called Newton's Scattering of Thermoelectric Materials. So this is the most important one, the Newton scattering, as it gives both some introduction to thermoelectrics and to Newton scattering. Finally, I have given you some background material in magnetism, which will be for the second week. So there's Advances in Magnetism, which tries to give an overview of the status of where magnetism is today. And the other one is more detailed about magnetic nanoparticles. This is basically the topics that I will go through during my lectures in Japan. So there will be a lot of focus on diffraction and scattering techniques in general. And then I'll talk about these techniques in the context of thermoelectric materials and magnetic materials. So I'm looking forward to seeing you all next week.